So how does this work? What is the visible universe made of? Well, we could say, well, God made the physical universe, and that would be the end of that, or so my 30 years of religious training would tell me. Or we could say, well, the universe is made of matter. We've drilled it down, we know what it's made of. It's not made of ether. It's not, we know the Earth is the center of the universe. Yes, it is. No, it is. Yes, it is. Okay. What is it really made of? Well, we break this down as physicists. Quantum physicists break this into protons, neutrons, and electrons. The first two we're going to talk about last. The last one we're going to talk about first. Well, we thought about this early on. Very, very brilliant people who supposedly broke new ground. Actually, I think we just remembered what we forgot. One very brilliant man, Niels Bohr, came up with a model which we call the Bohr model. It works mathematically very well at looking at matter and how it's built. It looks something like this. We have a nucleus. The positive ones are the protons, the orange ones are the neutrons, and you see the electrons going around it nice and neat in these orbits. Works very well when you're trying to calculate frequencies and atomic weight and all that, but that is not the way atoms really look. That's not the way electrons really work. In fact, you know, I'm a part of my job, I'm an electrical engineer, and one of the crazy questions to ask another electrical engineer is, what's electricity? And they go, what's electricity? Go on, you plug it in, you turn it on, electricity. No. What's the electricity that goes actually through the copper wire? I know we generate it and we use it, we change it into heat and photons of light, but really, what is electricity? Boy, they go, wow, I never really thought about that, what's electricity? Here's another one for you. We have an extension cord that stretches from here to Spokane. I plug it in here. How long does it take for the light bulb to turn on in Spokane? That's a good question. Does it go the speed of light? Does it go faster than the speed of light? Does it wait till the electrons get from here all the way up there on that copper wire before the light will turn on? Interesting question. We don't know the answer. But let's look at electrons. When we cool the universe down, we see that we don't have orbits like Bohr once said. We have what we call Heisenberg uncertainty principles. We have averages. We have probabilities of electrons showing up in certain places. There are two balloon-shaped orbitals we call s orbitals, and the rest of them look like balloons tied together in the center, called p orbitals. These are clouds. These aren't orbits. These are average areas where the electron is supposed to show up. And guess what? It doesn't orbit. It blinks out of existence and blinks back into existence, and there are two questions we still don't know the answer to. One, does the electron actually travel from point to point and we just don't see it? And the second one is that really the same electron as the one that blinked out? Or is that another electron that just kind of comes in like a tag team on every single atom, on every single molecule, in the chairs, in the bodies that make our bodies up, make up our DNA? We are actually exchanging energy for a molecule called ATP in our mitochondria right now. Well, most of us are because you're still awake, but wait till that lunch kicks in. A few of you will dip below the level of consciousness. So electrons are really very, very small points of energy that are negatively charged, that blink into existence around atoms. And we don't really know how to split an electron. We can capture them in an electron capture detector, but we have never learned to split the little beggars. So we just call them electrons, and we can reverse their spins, and we know how they behave, and they make great illumination, great computers, and awesome music. That's what we know about electrons. Now let's move on to the heavyweight. Let's talk about this thing, electricity, this energy that our planet pulsates with, that we see as a potential between the ionosphere of our planet and our planet. What does it look like? I mean, it's really intense. You know, we look at it and it's frightening and it's uncontrollable, and we are very careful when we plug things and turn things on, and especially when we open the back panel of things. Some people say, I really don't like electricity, you know. It hurts. I build electric trucks, and one of the things about that DC electricity, when you get up in the hundreds of volts, if you touch the two wires, it will shock you. It's quite an awakening. It also makes you younger, that's what I say. The proton, though, is the heavyweight. That's like the difference between this water bottle and James's farm. This is the electron, and James's ranch would be the proton. That's the difference in size. We look at the Earth rotating around the sun, and we could liken it to an electron rotating around a proton. And protons we're learning more about, but unfortunately we're learning about it like somewhat like a 6-year-old would learn how a mechanical robot would work. We smash it on the floor and see what pieces come out of it, and that's how we know the robot's made. Well, I'm not kidding. We're going to smash it right here. The protons, when we slow them down, we are looking for sort of a frozen picture of what this thing's supposed to look like. But when we slow it down and we put it in a detector, this is what it looks like. And this is a motion we call Brownian motion. You get a whole glass full of these things, and you drop a single dropful of ink in the water. Eventually, it will disperse through the water because of this motion. This is the kind of activity that we see on the atomic level. Well, we're interested in this. What makes this go? How does this stay so organized? How is one hydrogen proton like another hydrogen proton like another hydrogen proton? We don't know. Why does chemistry work the way that it does? We can take reactants of a specific number of protons and neutrons, molecular weight, and mix them together, and we can get reactants reliably every time. Why? What makes up the proton? Well, it's energy. Okay, what's the frequency of the energy? How do I get that energy? What do you form that energy out of? Good question. So, this is the dissection of a proton. We build a little thing called a super collider, and we take hydrogen protons and we pour them into a chamber, and